Yeah, good morning, everyone. So, yeah, I hope you had a good weekend and so on. Okay, so what I'll be talking about is first passage problems, both classical and quantum. So I've given some references. These are all for classical problems. So this is a really nice book by Redner, which is precisely on first passage problems for random walks. So this is, I really recommend it. It's written in a very physical way, but it's also very rigorous and so on. So this is really nice. This is an old article where some of the formalism was really developed. So it's a yeah, it's not very easy to read, but it's a good place to. And it's one of the first places where this was developed. And this is basically this paper, a review article. It's called Stochastic Problems in Physics and Astronomy, where he talks about random walks, like applications in various areas and so on. There's a small section which talks about first passage problems, specifically in one dimensions, and it has a kind of nice approach. Okay. In general, this article, it's also, again, it's very from just physics point of view, it's a very nice article on random walks, because everything is very physically explained and motivated. Okay, so these are just some reference. For the quantum part, I'll later give some references, but I think the first two lectures will mostly be on the classical walk. So let's start with so the first two lectures will mostly be classical, and okay, so let's start with the motivation for the problem. So basically, let's okay. So let me maybe first just give us a small quiz, like similar to what Jay Kumar does. So let's say we are doing a 1D random walk. Right. So in the like the preparatory schools, we discussed a bit about random walks, and one of the questions we asked is like, what is the probability? So this is space X, and this is a discrete random walk which evolves in discrete time. So one of the questions we asked is, what is probability of X after time n? Okay. So so this is probability. It's at some point X after n time steps. Okay. Now the first passage problem that we will discuss asks the question, what is the probability? So I'll call it P1. That's after it is at the point X after n time steps. Okay. So this is the first time it arrives at the point X. What is the probability that this happens after n steps? Okay. So this, I mean, initially people get confused that they are almost the same thing, okay, but they are very different objects. Okay. So I just wanted you to just quickly compute, let's say, what is P2 okay. So I mean, just try to compute these two objects just by enumeration, like what are the possibilities and what are. So I hope the question is clear, right? What is the probability that after four time steps, I am at this point for the first time, I am here. Okay, this is this question. And this question is, what is the probability that after 4 time steps, I am at 2? Right? So these are slightly different questions. See if you can figure out the answer. I'll wait. Sorry? So I'll wait for 2 minutes. Okay, what is the answer for this? Okay, 1/4. And this? No, you just have to count. Okay, so this is the, I hope the question is clear. What is the probability that I am at this place for the first time after 1/8? Okay, so let's see, someone said 1/8. Okay, so yeah, I think this is correct. So let's check. Okay, so now first of all, how do you find this? Right, this we discussed in the first class, that in the preparatory school. So if we take 4 steps, there are 16 possible walks, 2 to the power 4, right? And then we ask how many of those walks will reach 2, right? So here I've this is some space-time plot. This is space and this is time, and I start from 0, and this is x equal to 2. So I ask how many walks are there of 4 steps which end at this line 2, right? So the one walk can go like this. Okay, so this we know there has to be 3 right steps and 1 left step, right? And then the number of possible ways is 4C3, which is 4. So there are 4 possible walks which will end exactly at 2, right? So this is one walk is this one. The second one is you go 2 steps, then 1 left and then 1 right. That's 2 steps. Then you can go like this, like that, and like this. And then only if the first step left and all other steps right. Right? So these are the 4 possible walks. So there are 16 possible walks, and out of which 4 land up at exactly this. So 1/4 is the probability of, so that's how we get this 1/4, right? Now, how do we get this? Okay, so again, we have now, but so here now we have to ask what is it should be a first time arrival. Okay, so you see that out of these 4 different trajectories, like this one, it already arrived at this point at the second time steps, right? So it's not a first arrival. So if you think about it, like the only first arrivals are this one and this one, right? In all other cases, it has already arrived at an earlier time, so we shouldn't count those, right? So we should only take the paths which arrived here for the first time at a given number of time steps. Okay, so that's how we get 2 out of 16, which is 1/8. Okay, so this is the idea of the first passage problem. Okay, so now we'll ask sort of slightly. Okay, so here we can ask like what is the probability it arrives at for the first time at time step 1, at time steps 2, time step 3, and so on. And then we can ask what's the probability that it ever arrives at a given point. Okay. So if I want the probability that it arrives at some point, so what is my notation? At some point x, then this should be Okay, so this is the probability that it will ever arrive at this point. Okay, so supposing this walker just keeps walking forever, then you can ask what is the probability it arrives at this point at time 2 or time 3 or time 4 for the first time, right? And these are all, distinct processes. So if you sum over all n, clearly you'll get the probability that you ever arrive at this site, right? So this is, so this is the one of the questions we'll ask, that if you just keep walking, what is the probability that you will arrive at some location? Okay. So this is, if the probability is 1, it's called a recurrent random walk. Otherwise, it's called a transient walk. Okay. Okay. So, the kind of motivation for this is like, why do you study this problem? So one sort of motivation is so the random walk is also sometimes called drunkard's walk. Okay, so the idea is that supposing you are in a, you go to a pub and then you drink a lot and then you want to get home. So now, of course, after coming from the pub, you're doing a random walk, right? And then you ask, natural question is like, what is the probability I'll reach home? Right? And that, of course, is in 2 dimensions. Okay, so this is, let's say, okay, so this is the pub and this is your home. Okay, and you start walking from here, and of course you take, you're going randomly, and then you might just wander off far off, right? Or there's some probability that you might come back home. Okay, so this is the question, like, what is the probability you'll ever reach home? Okay, so, of course, in real life, it's not like a square lattice, infinite square lattice. It's first of all, it's a finite system. So of course, you'll eventually, if you keep walking, you might go to some country and then eventually come back. So on a finite system, you'll always come back, right? But we are asking on if it's on an infinite lattice, what is the probability you'll come back? Okay. So this is a question that that was first discussed by the mathematician Polya, and I think around 1940s maybe. I'm not sure the exact date. Okay, and he came up with a very beautiful solution. And what he showed is that if you are working on a 1 and 2 dimensional regular lattice, then the probability of return is always 1. But in higher dimensions, you may not return. Okay, so then the probability of return is kind of less. Okay, which makes sense because in higher dimensions, you have a lot of space to wander, right? So you can just wander off to infinity and never come back. But in 1 and 2 dimensions, you will always come back. Okay, so by the way, this Polya had, like, he was a mathematician, but he also was someone who was interested in kind of developing heuristic thinking. Okay, so he has a very nice book called How to Solve It. If you haven't seen it, I strongly encourage you to look at it. So this book basically tells you, like, solving difficult maths problems, like by just doing not very rigorously, but you get the exact answer by just doing things kind of heuristically. Okay, so now sort of another motivation for this doing this kind of studies is actually something I saw in Redner's book, where he discusses the problem of stock prices. Okay, so so actually it's quite interesting that the model of random walks was okay. It was first actually the random walk term was coined by someone called Carl Pearson in 1905. And he was basically interested in, so he was interested in understanding like how populations of mosquitoes evolve. Okay, so of course mosquitoes do random walks, and so a good model. I mean, he proposed that what they do is they just fly in some direction randomly for some time, then change the direction randomly and keep moving. And he actually posed a question in Nature, in the journal Nature, asking like, how do you find this distribution? Exactly this distribution after some amount of time, where does the population of mosquitoes look like? Okay, and this problem was then solved by by Rayleigh, who gave an exact answer for this question. Okay. But around the same time, I mean, there was also this model. I mean, random walks were being discussed in trying to understand how stock prices evolve. Okay, so the idea is that, of course, stock prices they don't seem like something which is doing a random walk. But in fact, if you look at, let's say, the log of stock prices, between which, so the stock prices, it changes from day to day. So let's say this is the stock price on the nth day. Now, if you look at the log of Sn, then it's actually quite well modeled by a random walk. Okay, so you can say that this +1 equals to log Sn plus some random variable. Okay, so I mean, so this model was, I think, proposed by yeah, so it's really interesting that at that time they had this kind of data, and they were analyzing, trying to understand it in mathematically. So one of the questions that people are interested in stock prices is like, supposing you know the stock price. I mean, so it's fluctuating, and what you might be interested in is like, so you buy stocks at some price, and then you want to know that, like, of course, if the price goes really down, it's bad. If the price goes up, it's good, right? So you might want to know, like, okay, how long should I wait to get a good price? Okay. So this again, basically, like if you are interested in like, okay, I'll sell my stocks maybe if it reaches some price or something. So you want to know like at what time typically will it reach some price? Okay. So this is again the first passage problem, like what is the first time the random walk reaches some value, right? Okay. So this is, I mean, this is another motivation to understand this kind of questions. Okay, so now what we'll do is, okay, so let's first try to discuss this, the polya problem, and find out what's the probability of starting from some place, what's the probability of reaching some point at a finite time. Okay, so this was already part of the problems in the preparatory lectures. So you must have many. So people did this already, or yes or no? No. Okay. Some people are shaking heads. Some people are saying. So anyway, I'll do it very fast. Okay. So okay. So first, what do we know about P of xn? Okay, so this we discussed that in 1D you can write okay, so you can write a, or let's write in any dimensions. So we can write an evolution equation for the random walk, which is given by. Okay, so basically we are looking at a random walk. So this is some site x bar, and it can jump to. So these are unit vectors. In 2 dimensions, it would be E1 hat and E2 hat. right? And I can jump in 4 possible directions, but in the d dimensions, there will be 2D directions. So these are the unit vectors where I can jump. Okay? And then we said like we can solve it using basically Fourier series, which is on a lattice version of Fourier transforms. So so then we defined I think P tilde. And the inverse of this is given by. So then if we just do the Fourier's transform this equation, then we get P tilde. Okay, so this is the solution after n steps. And then this we can find from the, so the initial condition is that the walker starts from the origin at time 0. So if you use that in here, then we get P tilde theta at time 0, which will just be 1, right? So this is equal to 1. And so this is the solution. Okay. And then we just plug this back in here and get P of xn. Okay, so okay, so let me just write this. This is one. Okay, so this is P of xn. Sorry, where is x? So e to the power minus I x. Okay, and then this one can work it out exactly in 1 and 2 dimensions. So in if we work this out, this gives the well-known result. And in d equal to 2 also, you can work it out. It's almost like this. It's just a product of 2 of this. Okay. But in more than 2 dimensions, this one can't do it. Then we know some asymptotics like large n, it becomes like Gaussian and so on. Okay, so this we won't discuss. Okay, then what we discussed is that from this quantity, we can evaluate something which called the mean number of visits to a site, right? So we said that, I mean, this walker, it keeps walking for some time n, then after, let's say, 2 time steps, after 2 time steps, what is the mean number of visits to this site, if I ask? So what is the answer? How will we find it after 2 time steps, the mean number of visits to this site? Okay, so basically you have to do is like you have to do all possible 2-step walks, which are like that. So there's probably, there's only one walk which will come here. and then you have to, so then the mean number will just be 1 over whatever number of walks. Okay, so, but we also derived a formula for the mean number of visits. Of visits. Okay, so mean number of visits to any site after n steps. This was, I don't know what was the notation, but maybe I'll call it V of x bar. So what was the formula? Huh? Right, yeah. So it was sum over, let's say, k at is time up to n p of x bar k. Okay, so using this, we can find the number. So I should put a n here maybe. Okay. So after n steps, this gives the mean number of visits. Okay. So I mean, so I gave a. So we discussed the proof of this result. I hope is everyone okay with that proof, or you want me to? Is the proof, was the proof clear? Yeah. Okay. Good. Okay, so this is the mean number of visits, right? And then if we put this n equal to infinity, that is like if you keep walking, then what is the mean number of visits to any site x, right? So that we'll just call it V x bar equals to V x bar for n infinity. Okay, so it's just some notation. I think last time I called it a capital M, but let's use this V. So I have some notes where I use this notation. Okay, so which I'll share later. Okay, so now, we'll find this object, and then what is good is that using this, we can relate this to this probability of return to a point x, to a first passage to a point x. Okay. So this is some quantity that is easy to compute because we already know P of xn, right? We have an exact formula for P of xn. And so then using that, it's clear that if we do this summation, so V of x bar is equal to, we take this and sum from n equal to 0 to infinity, right? So we will just get, so it's a binomial thing. So this will be 1 by okay. So this is the mean number of visits to a site X starting from the origin. Okay, so now we want to relate this to R of X, right? Which is the, so R of X is okay, so now how do we do this? Okay, so so let's first do relate V of 0 and R of 0. Okay, so the if you think about the mean number of visits to a site, let's say this site, starting from here. So so of course it starts from here, so it's already the number of visits is at least one, right? But then what it can do is it can, okay, it can go around, it can come back here. So that would be one visit. Okay. So what is the probability of that? Okay, so the probability of return is exactly R0, right? So V0 must be, okay, so I mean, it starts with 1 plus if it comes back once, then the number of visits is 2, and the probability of that is R0, right? And but it might come again, so it shouldn't. What's the probability that it does not come back? So that's 1 minus R0, right? So this is a probability of exactly 2 visits. Okay, and then you can ask what's the probability of 3 visits. So that is so that would be 3 times R0 square, and then it never comes back. Okay, and so on. So if you look at this, okay, sorry. So here I should have done this one should be 1. So this is it starts from here and never comes back. So it should be 1 minus R0. Okay, so so if we sum this, so 1 minus R0 is common. And then you have some series, which is 1 plus 2 R0 plus 3 R0 square and so on, which you can sum, right? So I think that's 1 by 1 minus R0 square. So that's the series is just 1 minus square. And so this gives you E0 by 0. So R0 is okay. So this is our basic formula for the first return probability. So if we know this, then we immediately know this. Okay, and so this is the probability of return to the same point. Now we can ask what's the probability of ever coming to this point. Okay, so in this case, what one can, so you can go here for like first visit, and then you never visit, right? So that's, so now we can write V of X. The mean number of visits to the site X is that you go once and then you never come back here. Okay, so this would be what? The probability of not coming back? 1 minus R0. So in principle, it should have been 1 minus, like this point is, of course, a different point, not this point. But in our case, it's a uniform lattice. So the probability of return to this point starting from here is the same as the probability of return from here, right? So we can use still use 1 minus R0. Okay, so this will be 1 into 1 minus R0. No, the transition probability can be non-uniform even for a Markovian walk, right? So even if you have Markovian walk, you can say these probabilities are some random numbers, right? Even then you can still use the same argument, but you would have to use a different, so you'd have to define a quantity which is like V of starting from X, what is the probability of return to X? Okay, so so let's say this is X to X. Okay, so right now we needed only to define 0 to 0 because for a uniform lattice, this will be the same, right? Any place is the same. So we only defined this, but in general, you can define something like this and it can be different at different sites. But it's not Markovian versus, it's all, I mean, this is, we are only, it can be Markovian, but different rates at different sites. Okay. Okay, so yeah, so here, what is the probability it goes to the site X, and then what's the probability it never comes back? So that would be 1 visit. Okay, so it should be 1 times Rx times 1 minus 0. This is clear, right? Okay, and then what will be the next term? 2 into Rx or Rx square? Rx, right? Okay, and then it comes back once, and then it never comes back. Okay, and so on. And this, if you do it, you'll get equals to Rx by 1 minus R0, I think. Rx is common, and then 1 minus R0 by the. Okay, but 1 minus R0 is just V0. So this is equal to Rx into V0. So we get a formula for Rx. Okay, so these are our two basic equations, which gives the probability of returning to the origin, and this is probability of arrival at some point x. Okay, so there are two notions. One is return, and one is like going to another point at a different point. Okay, which is like I'll call this arrival, and this is return. Okay, so so now basically we have to evaluate these quantities V0. We have very explicit formulas for Vx, right? So if we put 0 here, then it's some integral. There's no parameters, it's just some integral, right? So once we know the integral, we know some precise values. Okay, and then I think this was also part of the assignment, like to show that this integral is divergent in 1 and 2 dimensions. Okay, so now the question basically boils down to doing this integral Vx equals to okay, so d equals to 1. Okay, so let's find V0 first. Okay, and so this time without doing too much, basically you have to notice that if you look at this integrand, it is clearly divergent near theta equal to 0, right? And the divergence is, so if it is divergent, then you have to look at the small theta behavior. So small theta is d theta by theta square, and that is of course, I mean, this is a non-integrable divergence, right? So this is infinity. So you don't have to do much, it's infinite. So that's infinite. Okay, so but we just want to understand why it's infinite in 1 and 2D and finite in yeah. In 2D, okay, so let's again look at the integral 2 pi square minus pi 2 pi d theta 1 d theta 2. Okay, so of course, I mean, this is, I mean, integral in some, let's say some, in some theta 1, theta 2 plane, which goes from minus pi to pi. Okay, but here again, we notice that there is some divergence near the origin, right? So near theta 1 equal to 0, theta 2 equal to 0, this is, the integrand is divergent. So first we just want to understand it's, I mean, is it, I mean, is it still integrable or not, right? Even though it's like you can have a divergent integral, right? Dx by x to the power half, 0 to 1. Even though it's divergence, it's integrable, right? It's finite. So we just need to see what is the power here, okay? So now in 2 dimensions, because it's d theta 1, theta 2, so let's just focus on the integrand, like the behavior of the integrand in the small theta region, okay? So if you are interested in just the small theta region, then we might as well expand this theta 1, theta 2. So this would be then theta 1 square plus theta 2 square, right? So 1 minus this is so this is approximately equal to, so we can forget the constants and just look at this. Okay, and then we can like just try to go to like polar coordinates, because I mean, we don't care much about what happens outside, right? So we can, instead of a square, we can even replace it by a circle and do the integral in polar coordinates. So then we'll get theta, theta d theta, and theta 1 square plus theta 2 square is just theta square. Right? So, and okay, then there's a angular integral which will give some pi or 2 pi. Okay. And so, but now the main point is that this integral again is d theta by theta, so that's log theta, so it diverges at theta equal to 0, right? So it's definitely, there's no way you'll get a finite answer. So it's clear it's in 2D also, it's infinite. Okay. Okay, so this kind of arguments people should be very clear about. Okay, I mean, it's a very simple argument, but you should be clear of what you're doing. You're making some very simple approximations, but they are, it's very completely rigorous. Okay. Then in 3D, if we repeat the same thing, then the integral we'll get is, so we go to like radial coordinates, and we'll get, yeah. No, I'm not taking equal to, I'm just going from theta 1, theta 2 to, let's say, okay, I mean, if you call it x1, x2, okay, theta 1 to some, so theta is like now the radial coordinate, and then there's some angular coordinate phi. It's just changing from Cartesian to polar coordinates. Okay, so I mean, theta 1 square plus theta 2 square is equal to theta square, right? It's just changing coordinate system. I mean, if you find this confusing, you can just call it x and y. Okay, and this you call r theta, and maybe it's easier to see. Okay, so now in 3D we get theta d theta by again theta square, and now we see there's no divergence, right? So we'll get a finite answer. Okay, so it's clear there's no divergence. That is because the divergence gets killed by this phase factor. Okay. So in higher dimensions, this integral is going to be finite. And of course, in 3D, doing the integral is still non-trivial, but you can do it exactly. In higher dimensions, I mean, at least numerically, it's very easy to do the integral, right? And you'll get some finite number. Okay, so I mean, it's a good thing to just use Mathematica or something to just evaluate this integral in 1, 2, 3 dimensions and verify what we are saying. Okay, so okay, so basically what we got is this V0 equals to infinity. And in 3D, you can do this exactly, and the answer is 1.5 something. And equals to, Okay, if you increase dimensions, what is going to happen? D is going to the V naught value will go down, right? What is at infinity? Huh? No, it's not 0. If you put D infinity, yeah, it's 1, right? Because I think you can neglect this and then it's 1. So infinite dimension, it keeps decreasing and becomes 1. And so now R naught is 1 minus 1 by V naught. So from here we get, since V naught is infinity, so we get this is equal to 1 in dimensions 1 and 2. And in 3 dimensions, if you do this, this is some 0.34 something. And some smaller values in higher dimensions. Infinite dimensions, the probability of return is going to be 0. Okay, which makes physical sense, of course. Okay, so this, I mean, so here we are doing everything on like hypercubic lattices, but even if you take any arbitrary lattice, you can more or less do this calculation. It's very similarly. And for example, if you can ask like on a graphene, if I'm doing a random walk on a graphene lattice, like what are these numbers? Okay, so what will be the return probability? It will, huh? Is it going to be different from this or? It's going to be the same, right? You expect, I mean, like, because it's a large n thing, so it shouldn't depend on lattices and all. So eventually, because you will get this kind of, this expression will be more complicated. But then when you do the asymptotics, you have the divergence will still come from small theta, and so you'll still get the same result. But it's easy to repeat this for any arbitrary lattices, okay? But here we are doing just hypercubic lattices. Okay, so now what's the next question? Okay, so so the now next question is, of course, like we proved that we in 1D, if we start from the origin with probability 1, we'll come back to the origin. Now, a natural question is like, how long do I have to wait to come back, right? So in particular, what is the distribution of times to return here? And that is what we called as P1 xn. So this is the next object of interest. So right now, what we just evaluated is, let's say, our so this is, let's say, return to the origin after n. So I think I am mixing up notations. I don't know which is better. Okay, I think let's stick to this. What is the probability of return after n steps to the origin, right? And so what we just now discussed is this object. Okay. So this we evaluated by using this kind of relating it to this mean number of visits. But now let's try to find this object. Okay, so for Brownian motion, I think Sanjib already did this in his class. And what was the answer? What was the return probability to the origin for the Brownian walk? Huh? Levy. Okay, maybe Levy, but what was the form? Okay, right, yeah. Yeah, so basically here it will be 1 by n to the power 3 by 2. Right? So there was time was continuous, so it's 1 by 2 to the 3 by 2. So this is what we want to now derive. But in 1D and 2D and in any dimensions, what is this result? Right? Okay, so we'll use two different approaches to compute this thing. One is called the method of like renewal approach. Okay, which is very close to what we did just now. And the other approach is method of absorbing boundary conditions. Okay, any questions? Oh, okay, so okay, so we'll pretty much do this what we did just now for this the return time probability. So if we ask okay, so if we ask what is the probability it comes back to x to the same point after n steps, so it could have come back here after k steps for the first time. Okay, and after that, for the n minus k steps, we don't care like if it's a first passage or not, but it should be back at the origin. Okay, so let me just write some expression. So I'm saying probability it's at the origin after n steps is equal to, of course, it starts at the origin, and then let me write this. So then, what's the probability that for the first time in k steps, it comes back to the origin? And then, what is the probability that in the remaining n minus k, it is at the origin? Okay, so this is 0. Right. So I mean, so this is first time saying like it comes back here for the first time after k steps. After that, it did something. It might have visited many times, but it should be at the origin after n minus k steps. Okay. So then total steps is n minus k plus k, and I have to sum. Let's say k equal to 0 to n, so that so it could have come back here for the first time in one step, and then and then the remaining n minus ones it does something, but at the end it's always here, right? So this is then so this is the renewal equation. Okay. So again, what we see is that we are trying to relate this object, which is difficult to find, to something which we know already. Right. So is this clear? Okay, so now, okay, so this is for return to this origin. And if we ask, we can ask the same question, like if we are going to some site X. So what you can do is you can go here for the first time in k steps, and then the remaining n minus k steps, you just do that. Okay, so this need not be a first time, this can be anything. But you can see that this takes care of all possible processes to give this. Right. So in this case, what we'll write is P of 0. Okay, so this again is the same thing, right? So here, starting from x, what is the probability that after n minus k, I'm still at x? Okay, And because it's again a uniform lattice, x to x is the same as 0 to 0. So that's why I'm writing here 0. Right? So it's just almost the same argument as I used before. I'm just now I have a time index. Here, I mean, okay, so here, like at n equal to 0, I mean, I can't be at x. Yeah, so it still starts from the origin, but I can't have this term because at time 0, I can't have a term like this, right? At time 0, I can't be at a point x, which is not equal to 0. So, I mean, it has to be 0. So this term won't be there. That's the difference. Okay, you can, I think it should start from 1. Yeah, it doesn't matter. I can always set 0 to 0 as 0, but we can start from 1. Yeah. Sorry? It will be? Sorry, say again, I didn't understand. Yeah. Oh, k will be, yeah. I mean, so whenever it's not, yeah, it will be 0, right? For odd k, it will automatically be 0. But we can write it more generally. Let's see what I wrote here. Okay, see here, I mean, it doesn't matter if I write 1 or 0 because I can, T1, 0, x is always 0. So I mean, that's, so let's just write 0, 2, I mean, this doesn't matter. Okay, so now how do we solve this? So we have some kind of connection between this equation. So how do we solve this equation? Okay, so basically, so here n minus k, this is really time, right? So we have a kind of a convolution equation in time, right? So if you think of the continuum, you could have done the same thing. There you would have something like p of xt equals to p1, some, let's say, p prime x. Okay, so this is what we would have got if we had done continuous time. Okay, so now to solve this equation, what would you do? Laplace transform, right? So we'll do the like analog of Laplace transform in discrete time, okay, which is like you define something called generating functions, but it's basically just doing Laplace transforms in discrete time. Okay. So yeah, so this is the continuum. So everything what we're doing in the discrete time, you can also do in continuum time. It's a trivial extension, but we'll mostly stick to the continuum thing. Okay. So this I'm just writing so that, I mean, people just recognize that I think people are more familiar with Laplace transforms than with generating functions, but it's essentially the same thing. Okay, so basically we'll now use the method of generating functions to relate the generating functions of these two objects, right? Of the first passage with the regular probability. Okay, so basically we'll define this, what is the notation? F and G. Okay, so we'll define two generating functions. So I'll call them G of uh, Okay, so these are the kind of Laplace transforms for P and P1. Okay, and if we just take this equation, multiply it by z to the power n on both sides. So here, so it's, let's say, into z to the power n. This is z to the power n. Here, what we do is z to the power n, but we write it as z to the power k times z to the power n minus k. And then there are two summations. So it will be like product of two generating functions, right? So what we get is, so from this equation, it will be G G0Z and from the first equation, it's G of G0, right? Because this is G0Z. So this is okay. So this is the final. If we put z equal to 1, we get recover exactly what we had got earlier for R0 and Rx, right? If we put z equal to 1. Okay, so now this G0Z and GXZ we already know. So what is it? Okay, so basically G, okay, this was V of X, but so G of, right, so from the expression for Pxn, if you do z to the power n, then again you'll get some geometric series. If you sum, you get this, right? I think this is correct. Let's see. Yeah. Okay, so I hope this is clear, right? Okay, so now from this, we can then find f of f0z. And okay, so now the question is, okay, so it still looks quite complicated in general, right? I mean, we said that we can't do these integrals exactly and so on. And then finding this is also looks complicated. So, but what can we extract out from all these complicated forms, right? So the basic question now is, okay, so we can write these formal expressions. Now what we want eventually is, so let's say f of 0, z. So this was what equals to, is equal to sum of p 1 n 0. Okay, so somehow we have managed to find f of 0z, but what we are interested finally is in this object, so we have to invert this, right? So this is like inverse Laplace transform. So that, of course, formally we know exactly what to get. So P1 N0 is what? What is the inverse of this? Huh? Derivative of what? Uh, oh, you're saying if we know this, if we take derivative and then we can find this. Okay. Yeah. But is there a formal expression of, can I invert this? Ah, yeah. So you can write a contour integral, right? So I think it's some 1 by 2 pi I. Huh? Then here what? I think z to the n plus 1, right? Okay, so it's some contour integral. Okay. So this, of course, looks very complicated. First of all, G itself is complicated. Then after that, you have to find F, and then I mean, there's something divided by something. So it's going to be very messy, right? So in general, we can't find this. But typically, what we are interested is in, like, at large n, how does this quantity behave? Okay. So it turns out that for that we can still say something useful and very concretely. So let's try to understand this how one can do this. Okay, so this again, this Redner's book is a good place to read about this this method. Okay, so it's again kind of heuristic, but it works. Okay, so the idea is, let's say in general, so you have some, you define some function a of z is equal to then some. Okay, so this is how we define the generating function, right? So now, given this, what we want to say is, can we say something about the behavior of this at large n? Okay. So now, one way to do this is to so supposing I put z equal to e to the power minus s. Okay, so then this becomes. Okay, so far no approximations. Okay, so now if I'm interested in large n, then okay, so what did I do? Z equals to minus s. So the large n behavior, then this function will die down very fast, right? And if I want to get properties at large n, what I should do is look at very small s, right? Otherwise, I mean, it has no information. So if I want to understand the function at large n, then I should look at small s, right? So Okay, so I've defined this new function a tilde s is basically a of. Okay, so either one can look at z close to 1 or s very small, right? They're equivalent, but it's convenient to define this function a tilde s. Okay, so now, yeah, this actually looks closer to a Laplace transform. Okay, so now if you are interested in very small s, and so this sum will extend for very large values of n, so you can kind of you can replace it by an integral and write it as 0 to infinity d of n. Okay, so this is of course approximate, but so this is really the idea of doing heuristics. Okay, I mean, and it usually works, but once in a while it won't work. But if you are careful, you can make it work. Okay, so we write it like this. Now, what you see is that this integral, like up to where will it be significant? Like till it's a decaying integral, right? As n becomes large, it becomes very small. So up to what n is it significant? 1 by s, right? So we can again write it as 1 by s. Okay, so I mean till 1 by s, it's almost constant. So this is, I mean, we might as well write because till 1 by s, this is almost constant. Okay, I mean, so it's it looks like I'm doing random things, but it works. Okay, if you think about it, why it works, I mean, it's interesting, but it's something it works. So now we have something like this. So then we can see that at large n, you can replace s by, let's say, okay, let me change. This is a dummy variable n, so let me call it n prime. Okay, and now supposing I replace s by 1 by n, so a tilde at 1 by n is approximately equal to. Okay, and now what we can invert this. If we take a derivative with respect to n, then we basically get. Okay, so this is what we'll do. Okay, so what do we have to do? Basically, given this, so if somehow we find this a of z, it looks very complicated, but then we look at z very close to 1, okay, which means or s going to s close to 0. Then we can do, maybe we can evaluate the integral somehow. And once we know that integral at values very close to z equal to 1, then we just take a derivative of this function and then we are done. Okay. So let's do, okay, let's see if and let's do some examples. Okay, we have 15 minutes. Okay, let's at least do one example to see how this works. Any questions about this? Okay, so let's do the 1D example, d equal to 1, where we already know the answer, what to expect. So if in d equal to 1, so first we need g g of 0 z. So this is, I mean, 1 by 2. Okay, so this of course you can do exactly, but we won't do it exactly. We'll do it in an approximate way and try to extract the information in using that method. Okay. So now we just want to look at z very close to 1. Okay, so at z equal to 1, this is a divergent integral, right? We just saw it, it's infinity. But if z is very close to 1, then the leading contribution to this integral will come from theta small, right? Close to 0. Okay, so if we look at this z close to 1, then we can approximate this. Okay, and see, because the divergence is all coming from small theta. Okay, so we don't care the upper limits and so on. So here you can even put, let's say, minus infinity to infinity. Okay, so you make some mistake, but we don't care about those mistakes. So now this integral is, so this is some constant. Okay, so here there's some constant which we don't care about too much, but there's some constant. But the integral is 1 minus z and then plus z theta square by 2. And we're looking close to z equal to 1. So here we can just put this 1. So now, and we are interested in the z dependence, right? That's the most important part. Like how does it depend on z, this integral? Okay, so now there's a cheap way of doing this integral. If we just want the z dependence, okay, so that is scaling. Okay, so you can scale out this factor 1 minus z, right? So if you divide by 1 minus z, then what do you get? So this is, so I'll take out the 1 minus z outside. So some constant by 1 minus z. So this becomes 1, and this is 2, 1 minus z. Okay, then so here we can replace theta by square root of 1 minus z as some new variable. So we can introduce theta by square root of 1 minus z and multiply by square root of 1 minus z, right? So now if you replace this some new variable theta tilde, then we see that this integral does not depend on z. So the z dependence is entirely here. So we'll get something like this goes as some constant divided by square root of 1 minus z. Right. So, yeah, what we really need is the z dependence. There are some constants which right now we don't care about. Of course, they are important for some things, but right now the z dependence is the crucial part. So z equal to 1, you can see it blows up as is expected, but we have some explicit thing. Okay, so this is g of 0z. Okay, so I should, it's not exact, right? So I should always put something like this. So therefore, if okay, and okay, so now if we use this, so f is like this function a of z, and now we can get our a tilde s. S is just replace z by e to the power minus s and take small s, so that is root of s. Right. Okay, so now we have we said that P1n. So you put 1 by root n and then you take a derivative with respect to n. So this goes as 1 by 1 by. Right. Okay. So we have recovered what we like. I think Sanjib had earlier derived for the Brownian motion. Okay. So in this case, I mean, it turns out that you can do this integral exactly, and you can also find this exactly. And so we'll maybe write that in the next class, and you can get a more exact formula for P1 and 0 for the 1D random walk. And but this is one way to, if you're just interested in asymptotics, this is the way to do it. Okay. Because in 1D, well, you can do things exactly, but in higher dimensions, there's no way. But this method is very powerful. Okay, so I think oh, there's still time. Okay, 10 minutes. So in okay, I think maybe I'll do the higher dimensions in the next class. But what we'll find is that okay, so this is okay, so this is what we'll find in higher dimensions. So 2 dimensions is slightly non-trivial, and 3 dimensions it's looks like this. So in particular, we should compare this with let's say uh, 0. So if you ask like the usual random walker, the probability of being at the origin after n steps, then in 1D, what is it? At large n. So if for this quantity, how does this decay with n? So this is the first passage, right? This is the usual probability. Into the power 1 by into the power 1 by 2. So it's 1 by n half. Right, because the random walk is e to the power minus x square by n by square root of n. Right, in 1D it's this, right? So if you put x equal to 0, it decays 1 by n. In higher dimensions, this formula becomes what? This becomes like d by 2, and this is as vector. So even if you put x equal to 0, it's 1 by n to the power d by 2, right, in any dimension. So so if you do this quantity, it will look like 1 by n. Okay, so again, this is equal to 1. Okay, so basically you can see that in 1D there's a drastic difference between the return time and the usual probability. In 2D there's a logarithmic correction to this, while in 3D it looks almost the same, right? The reason is in 3 dimensions anyway you don't come back so often, so that's why this result doesn't change so much. Okay, so okay, so what we'll see in the next class is that using this kind of a method, you can actually work out this asymptotics nicely, even though like the exact things can be computed only in 1 dimensions and so on. Okay, so so this is what we'll do in the next class, and then we'll discuss this other method of absorbing boundary conditions. Yeah. No, sorry, say again. So I defined A tilde of S as A where Z is replaced by e to the power minus S. Right? So A e to the power minus S. So if I replace Z by e to the power minus S and then take small s, right, then it's root of S. Yeah, that's all. Okay, any other questions? No. Okay, so okay, then I think it's a good place to stop.